All right, guys, so what we're going to do is look at this curve sketching to start. And basically what I want to talk about is how did you know how to get your graph? And unfortunately, the first time I did my first graph, I thought I was supposed to draw my graph on top of the original. You are not. So this was actually, this is in 3.1. I went backwards a few days. I posted this, the answer key to this maybe. Good to do this, didn't you? Okay. Like yesterday. That's pretty a review, right? Okay. It's all a blur. Okay. Well, then we won't go over too many of these. So basically, like what I did is I kind of picked my intervals, determined if it was increasing, and then determined that was positive. When I'm graphing these, I typically start with graphing the zeros of the function. So like if I was up here and I was like, oh, the derivative is 0 at -3 and 2, that is the first thing I graph on my derivative graph is the zeros. So like down here for this graph, I looked at it and I was like, oh, okay, I'm going to have an extrema at, this point and that point. So then down here, I plugged in my zeros. Now, -1 is an extrema on the original, but on this graph, it's a 0 where it doesn't cross the x-axis. And it doesn't cross because this graph is still decreasing. So it's kind of like a blip extrema in the sense that it is a change or an extrema, but not a change in sign. Okay. So that was the curve sketching. So yesterday, did you do the AP calculus review packet? I thought we were doing that in person today. You submitted the differentiability FRQs, right? This one? Yeah. One, the continuity and differentiability, because when I was grading our chapter 2 assignments, one of the things we weren't really grasping was continuity and understanding the rules behind it. So something like number 1A, that is not continuous. That is a piecewise function in which we have jump discontinuity. It jumps from the point down here to the point up there. So even though this dot is filled in, that is not a continuous function. So even though f of -1 exists, because the limit at -1 does not exist, it is not continuous. Same with here. The limit as x approaches 3 might exist, but the function does not exist because there is a hole at 3. So f of 3 is not in its domain, therefore it is not continuous. Letter C would be continuous because I can draw that curve without lifting up my pencil tip. Same with letter D. You could trace that curve without lifting up a pencil tip. Letter E, the limit at 2 does not exist. That is called infinite discontinuity. Letter E is infinite discontinuity. Letter F is also infinite discontinuity because you have a vertical asymptote occurring. So even though there is a point for f of 0, the graph does not meet at that point, therefore not continuous on its domain. Not continuous, there's no f of 1. Letter H, again, the limit from the left and the right exists, but the left and right hand limit do not equal the function value. Therefore, since the limit doesn't equal the function, it is not continuous at x equals 0. The limit does not equal the function, therefore not continuous at x equals 0. Letter I, f of 4-ish does not exist. You could have maybe had a lesser number, that's fine. Jump discontinuity does not exist. Letter K, that is where the limit doesn't equal the value. And example L, that's not a function. If it's not a function, it can't be continuous. If it's not a function, it can't be continuous. This fails the vertical line test on multiple occasions. Okay, so now we're getting down a little bit more into, do you know what a graph looks like and do you understand it? So x cubed is a continuous polynomial. 3 to the x is a constant raised to a power. So there are no numbers that you could plug in for x that would not have a value. So this is continuous everywhere. There are no values for x that I could plug in that would not work. In example B, I have 2 vertical asymptotes from that denominator. I have x squared minus 81, which factors to x minus 9, x plus 9. Therefore, I have 2 points of discontinuity at 9 and negative 9. Same with C. Even if I could factor this, so if you factored your numerator, you get x plus 6, x minus 4. So yes, even though the top is x minus 4, x plus 6, and the bottom is x plus 6, x minus 6, the x plus 6's would cancel, yes. However, when you cancel them on that graph, there is still a hole at x equals negative 6. So just because you have a removable point and you can, factor and simplify, when you graph it, there's still an error or an undefinedness at that point. So a negative 6 is still not in my domain, even though they factor and cancel. And I think that was one of the issues we are having, is we are seeing it as a point that did exist because they factored and canceled. And then the tangent is made up of many, 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 many asymptotes at all intervals of n to the pi halves. Number 3, find where the function is continuous at the value where the rule for the function changes. So for number 3, I was taking that breaking point of 2 and plugging it into the top and to the bottom. So we were seeing if 8 minus 2 squared was equal to 6 minus 2. So in this case, is 4 equal to 4? Yes. So because 4 was equal to 4, we could say it was continuous. Over here, you have 4 minus 1 squared equals 1 plus 1. Well, 4 minus 1 is 3. 1 plus 1 is 2. Does 3 equal 2? No. Therefore, not continuous. So basically, we're looking at these. We know they're piecewise graphs. We don't need to actually graph them to understand continuity. We just need to look at their breaking points and determine if they meet each other at that breaking point. They're all polynomials, so polynomials are continuous everywhere else. So again, our only point of concern is at the breaking point. So you did the same thing with letters D, E, and F. Now F is a little bit different because F has 2 breaking points. So in letter F, you had to investigate the breaking points by understanding which point came from where. So when X was 0, Y is 3. And then up here, when X was 0, we had to understand that that was not going to exist. So that's a case where you would have to have factored. So that you could find the limit, because we know that the function doesn't exist there. That's why it's not in the original domain. So we take out a factor of x, and then up top you can actually do x minus 1, x plus 1 over x minus 1, because we know these x's canceled. So now when we're trying to find what these two are approaching, their limit is what's approaching x plus 1. So 0 plus 1 is 1. So 1 and 3 are not the same, therefore not continuous at 0. However, 1 plus 1 is 2. At x equals 1, it's at 2. Hence the continuous at 1. Okay. Pausing all of that, are there any questions on anything we've talked about so far? Does anything I say not make sense? Are we confused at all? Because I know the next part is where we probably started to have some issues, right? Wrong? I'll let you guys check these 6 problems rather, and then any of those problems you want to go over, I will go over for you. So Nick and Caitlin, that pertains to you as well. Come on, Nick. I'm kidding. What'd you say? Anybody else want to see F? Those are so quiet. Let's do F. All right, stop share, and then I'm going to open up a whiteboard. Okay, so in example F, you have, there we go. A squared minus x squared. So you're going to plug in 2 for x squared. So you get a squared minus 2 squared. And then we have 1.5a times 2. So we know that in order to be continuous, I need these 2 points to equal each other, because in order to be continuous, the jump or the break point has to equal the other jump or break point. So that gives a squared minus 4 equals 3a. And then that's a quadratic, so it's a squared minus 3a minus 4 equals 0. So then you get a minus 4, a plus 1 equals 0. And then I get a equals 4 and a equals negative 1. So what that means is that there are 2 values of a that would make this true. I could say that f of x equals 4 squared minus, 4 squared minus x squared for x less than 2, and 1.5 times 4x for x greater than or equal to 2. And again, you could have cleaned it up. You could have said 16 minus x squared, and then you could have said 1.5 times 4, which is the same as 3 times 2, which is 6x. And then checked yourself and plugged in your numbers and saw that they worked, because 16 minus 4 would have given you 12, and then 6 times 2 also gave you 12. Does that make more sense? Okay, so back to our handout. So once we get through these few examples, we're going to move from continuity to differentiability, which is the main topic of chapter 3-2. But again, we had so many issues on chapter 2 with continuity. I thought it was important to really go back and look at these types of generic equations. So here you had to make a relation between the two. So you got a was equal to b minus 1. Here we had to make that same connection, now adjusting for the fact that a was negative 1. So if a was negative 1, then b was 0. And then here it wanted you to just find any point. So if I said b was 4, what did a have to be? If I said b was 11, what did a have to be? Okay. For 6, the graph of the function f of x equals x plus 4. Find what it appears to be approaching. So as it's going towards 2, it appears to be 6, but it's really infinite. Number 7, sketch a function having the following attributes. Has a value of f of 2, so that meant you needed to have a point, a limit as x approaches 2, but is not continuous at 2. So we needed these to match up, but the point to be elsewhere. So there is like a open circle here, and it's kind of hard to see. And the value is down there. So where that red dot is, it would be an open circle. In letter B, it says has a step discontinuity. Step is the same as jump. At x equals 3. And f of 3 must equal 7. So here's kind of like my 7 and my closed point. Here's my 3, and then there's my open point down below. Now again, you could have had a totally different looking graph. You could have had a graph that looked like this. So here's your 3, here's your 7. This might have been curved down like this. Could have had an open circle here and an arrow there. It didn't say if f of 3 equals 7 occurred from the left or from the right. It just asked you for that jump discontinuity and for there to be a point. Letter C, the limit as x approaches 4 was equal to -2. So I did need to have a -2 and a 4 with an open circle at those points approaching that value, which meant that the line had to exist on the left and the right. So this one, it really wasn't open to all that interpretation except for maybe your line being a little different. Like maybe it came from here and went there, or it could even have been like this. But the overall idea and understanding was that it needed to equal from both sides and be an open circle at that point. Okay, in letter D, you know you needed the point -2, 3, but there had to be no limit. Therefore, you were looking for a discontinuity and no vertical asymptote, which meant this couldn't go down like this. Now we're getting into continuity and differentiability together. So in letter A, this graph is continuous. I can draw it without lifting up my pen. However, at this point right here, we have a sharp change in direction. It goes from kind of being this, smooth quadratic-y looking function to linear. So even though they match up, it is not differentiable at that point C. So it's continuous but not differentiable. Letter B, it's neither. Letter C is neither. Letter D is, actually that should be changed. So if my C value is over here, D is both. Because at C, there is no area or issue. So it says at x equals C. This C is neither, 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 both. You will never just see the word differentiable. So if it asks you to state continuous, differentiable, both, or neither, it'll never just be differentiable, because differentiability implies continuity on the function before it. So it will never be differentiable but not continuous. It will never be differentiable but not continuous. So that kind of even hinted at letter D on this example here, where it says make a graph differentiable but not continuous. It's impossible. It cannot be differentiable but not continuous. That is impossible. Differentiability implies continuity. Continuity does not imply differentiability. All squares are rectangles, but not all rectangles are squares. All functions that are differentiable are continuous, but not all continuous functions are differentiable. Okay, for each function, show work to determine whether the function is continuous or non-continuous, differentiable or non-differentiable, and sketch the curve. Show work necessary to prove your statements. So again, in order to show something is continuous and not differentiable, differentiability comes from taking the left-hand limit and the right-hand limit at the derivative and showing whether or not the derivative limits are equal to each other. So like that's what this line right here says. It says that the limit as x approaches 0 from the left of f of x equals the limit as x approaches 0 from the right of f of x. And it says that the limit as x approaches 0 from the left of f of x minus f of 0 all over x equals the limit as x approaches 0 from the right of f of x minus f of 0 all over x. I ran out of room. So these represent two different limits. This represents the limits of the values, and this represents the limit of the derivative. Okay. So I think 11, A, B, and C are kind of where it gets that trickiness to us again, because we look at them and we're like, why are there like 7 letters in there? I don't know what to do. So again, what I want to do is go over some of those with you. So anybody have a preference on whether I do A, B, or C? I'm going to do all 3. What? Did you say A? All right. So at a minimum, I'll do at least 2 of them, because I think, again, like, I think these are the tricky things. And yes, so let's look at them all. 11a. So we have f of x equals x cubed and x greater than or equal to 1. And then we have a, x minus 2 squared plus b for x less than 1. So the very, very first thing I need to do is look at continuity. So continuity comes from the top equation equaling the bottom equation at the breaking point. So I'm going to look at 1 cubed equaling a to the 1 minus 2 squared plus b. So that gives me continuity. Without continuity, there is no differentiability. So I get 1 equals 1 minus 2 is negative 1, but negative 1 squared is 1. So I get 1 equals a plus b. So what that means is, in order for this function to be continuous, I need the relationship that when I add a and b together, they equal 1. That has to occur. In order to be differentiable, I need the limits as x approach 1 from the left using the alternate form of the derivative. So that would be like x cubed minus f of 1, which we said was 1, over x minus 1. I need the left-hand derivative to equal the right-hand derivative. So it's f of x minus f of 1 all over x minus 1. And that's using the alternate form of the derivative. So now I need to clean this up. So in order to clean this up, you could use your sum or difference of cubes formula. So if you recall, a difference of cubes always factors as x minus 1 and then it is x squared. It changes signs, so it becomes plus this, the first term times the last term, which in this case would be x plus 1 squared. So then the x minus 1's cancel. So you get the limit as x approaches 1 from the left of x squared plus x plus 1. So it's like 1 plus 1 plus 1, which is 3. So the left side has to equal 3. The right side, this becomes a x squared minus 4x plus 4 plus b minus a minus b all over x minus 1. All your b's cancel. I did do that right? Yep. And then you distribute. And now you can do factor by grouping. So if I rearrange these two terms here, it's kind of like, and I'm just running out of room, so that's why I'm doing this. It's kind of like saying negative a plus 4 all over x minus 1. So if you group your first two and you group your last two, I can take out an ax, and I might have to move over that one in this one. I have to rearrange my terms one more time to put an x over here. So that would give you x minus 4 of an a, and that leaves me x squared minus 4x plus 4 minus 1 all over x minus 1, and then that leaves you with a, and here plus 4 minus 1 gives you 3. So now you can factor that as x minus 3, x minus 1 all over x minus 1, and then your x minus 1's cancel. Hallelujah. I have 3 equals the limit as x approaches 1 from the right of a to the x minus 3, because I just brought up what was down there into the corner to save my space. Now I can take my limit because there's no denominator issues, and I get 3 equals a 1 minus 3, or 3 equals negative 2a, which means a equals negative 3/2. Once I know what a is equal to, I plug it back in over here, and I get 1 equals negative 3/2 plus b. Add that negative 3/2 to the other side as a positive. 1 plus 3/2 is 5/2. Let's do example B. And I'm going to use, so this one I did the alternate form. The other one we're going to do the formal definition. So once again, the first thing you need is continuity. So I need a 2 squared plus 10 to equal 2 squared minus 6 times 2 plus b. So I need 4a plus 10 to equal negative 8 plus b. So at the end, once I do my derivative, I need 4a plus 10 to equal negative 8 plus b. So we're going to look at the limit as h approaches 0 for the top part of this equation. So that's a x plus h squared plus 10. So it would be f of x plus h minus f of x all over h. So again, we're going back to the formal definition of the derivative. And then you have the limit as h approaches 0 of ax squared plus 2axh plus ah squared plus 10 minus ax squared minus 10 all over h. Ax squared and ax squared cancel, 10 and 10 cancel. So I am left with 2axh plus ah squared all over h. So I can take an h away from all three terms. And that leaves me with the limit as h approaches 0 of 2ax plus ah. Plugging in 0 for h, I get that this has to equal 2ax. So again, because this is coming from the top, this is the right-hand derivative because it is for x greater than or equal to 2 on the original. So this is the right-hand derivative. It's for all the x values greater than or equal to 2. So the derivative for x greater than or equal to 2 is 2ax. The left-hand derivative for x values less than 2 is the limit as h approaches 0 of x plus h squared minus 6x plus h plus b minus x squared plus 6x, because we distributed our negative, minus b all over h. Now you have to FOIL. So we get x squared plus 2xh plus h squared minus 6x minus 6h plus b minus x squared plus 6x minus b all over h. So my x squareds cancel, my 6x's cancel, my b's cancel. I'm left with the limit as h approaches 0 of 2xh plus h squared minus 6h all over h take away an h from each. And you have 2x plus h minus 6. Plug in 0 for h, and we get 2x minus 6. So what that means is in order to be differentiable, I need two things to occur. I need 2ax to equal 2x minus 6, and 4a plus 10 to equal negative 8 plus b at the point of concern, which is x equals 2. So I can get rid of my x's here. So 2 times 2 is 4a. 2 times 2 is 4. 4 minus 6 is negative 2. Divide by 4. And I get a equals negative 1/2. So at x equals 2, a has to be negative 1/2, which means b (4 times negative 1/2 is negative 2. Negative 2 plus 10 is 8. Add 8 back to the other side, and I get b is equal to 16. Was everybody able to follow along and kind of see what we were doing there? Fantastic. I think now that you know how to do that, I don't want to do letter C now. I want to give you guys some time to kind of work through and look at everything. So that kind of wraps up what I think you had to turn in, besides the differentiability handout, which I'll post the answer key to. What I had scheduled for today was kind of the AP Calc AB review, which I know, Nick, you started to do that and you asked me about 13. Did you figure 13 out, or do you want to see 13? Okay. So is everybody else going to know the next few pages in that packet? So it says AP Calc, AB review, continuity and differentiability AP questions. So down on number 13, I want to go over that one real quick. And if anybody worked on it and has questions on other problems, I'll gladly go over those as well. I am going to post the answer key to this so you guys can use it to study. So limit as h approaches 0 of sine pi halves plus h minus 1 all over h. Let's talk just real quick what this even means. So this is asking me to find the derivative of the function f of x, where f of x is the sine of x. It's asking me to find the derivative of sine x. And it's asking me to find the derivative of sine x at x equals pi halves. So when we simplify and clean all of this up, what we are actually finding, or what that answer is representing, is f prime of pi halves, given that f of x was sine x. And that should make sense because f of pi halves, which is the sine of pi halves, is equal to 1. And that's what you're seeing right here. This is the alternate form of the derivative in a sense where it's f of x plus h minus f of x. And in this case, x is pi halves. So let's go back to the actual problem at hand, which is, what do I do with this sine of pi h plus h? So we need to use the sum of cosines and sine rule that says it's the sine of pi halves cosine h plus sine h cosine pi halves minus 1 all over h. And then you're going to take sine of pi halves and cosine of pi halves and turn them into their trig values. So we know sine of pi halves is 1, so that leaves cosine h. We know that the cosine of pi halves is 0, so 0 times sine h goes away. So now we're left with minus 1 all over h. This is really close, but not quite my rule. So what we have to do is factor out a negative 1 from our numerator. So that becomes negative cosine h plus 1 all over h. And you could rearrange your terms. And recall that the rules for limits say that if you have multiplication, this is the same as the limit as h approaches 0 of negative 1 times the limit as h approaches 0 of 1 minus cosine h all over h, which is our rule, which is 0. 0 times negative 1 is 0. So what that means is that the derivative of sine x at pi halves is 0. Better? You're welcome. Anybody else do any of those problems and want to know answers to anything, or any homework problems, or just any problem in general you came across and you were like, I have no idea? So for tomorrow, guys, by, let's say, I'm going to say 8:30. That way we can go over it in class. I'm going to add an assignment on here. I want you to upload for me this AP FRQ question. So it says 3.2 differentiability AP questions. You're going to click that, and that should be these two FRQs. I want you to try these and upload those as your homework for tonight, due tomorrow. So if you didn't do this yet, this is what you're doing for tonight, due tomorrow. And that AP continuity packet. So does everybody have that AP continuity packet? This, you don't. It's only on Fusion. Because that's what I technically had changed for you to do tomorrow. And the packet in your packet I wanted to do today. So this is on Fusion. Like you three, I could print it for because I could print it. But like you guys at home will have to print this out and do this. Or do it on notebook paper. And then the other thing you should have done for tomorrow is the AP stuff we're doing right now, which is no, that's what you uploaded. No, that's the one I just opened. That's the FRQ. Yeah, and I don't think... Okay, so the two assignments you need to have uploaded for tomorrow are the FRQs and this handout right here. And if you already uploaded this, that's fine. If you have not uploaded this, this is like your homework for tonight, the FRQs and these 13 questions. It is the AP Calculus AB Review, and on Fusion, it is literally titled 3.2 Continuity and Differentiability Review.